haven't met most of you guys, so I'll introduce myself to begin with. I'm Jake Lipinski. I work for Atkinson Electronics. We supply the Phoenix valves for this project, which is your laboratory airflow controls. This is a standard Phoenix valve. Now, I don't know what experience level you guys each have with Phoenix valves, so I'm going to kind of explain what they are, go through the basics. If you feel it's too basic, feel free to tell me to skip ahead. If you feel you want to know something that I seem to be missing, ask any question you want. But basically, the reason you go with a Venturi valve like this versus a VAV for laboratory airflow control is so that you can control the airflow more accurately. This is a Venturi valve design where, as this cone moves in and out, just grab the clutch here and slide it in and out so you can see what's going on. So you can see the cone moving in and out. And as it moves in and out, the air flows around this gap and through the valve. Because of the shape and the design of that, it creates a Venturi effect, which ends up making sure that it controls the airflow much more accurately than a regular damper would. And the reason these work is because of this little spring inside here. I don't know if you guys can see it from there, but you're welcome to come up right after. I can show you each the inside of this and how that works. But this spring is not just a linear spring that has the same resistance across the whole path. It varies based off how hard it's being pushed down. So the harder it gets pushed down, the more resistance it starts to supply. That means that this can be maintained its airflow for a larger range of supply pressures. The valves are designed specifically to have between 0.6 inches to 3 inches across the valve of air pressure. There's some ports on the top of these right here which can be measured. So your air pressure from the inlet side to the outlet side needs to be at least 0.6 inches in order to maintain the correct airflow. If it's not that, then the valve goes into alarm and you'll see a flow alarm in your system indicating that I don't have my pressure drop, I can't guarantee that you're getting the airflow you want. It will still attempt to control and do the best it can, but once the physical requirements for the valve aren't met, obviously it's going to say, hey, I can't necessarily guarantee you're getting what you want. And the maximum it goes up to is 3 inches of pressure drop across the valve. Typically your system gets balanced so that it meets those requirements, and as long as you're maintaining your duct static pressure, everything's good across there. Now most of these are going to have, actually in this case you got Solaris only in this building, so all of these will have an individual circuit board on them. There are a couple other models that aren't in here that have slave devices and those kind of things. But in this case, each one of these is going to have a circuit board on it. It's going to be a LAN-based controller that communicates through Jace, and then all that information gets passed on to the Utah YAMAS control system, and you guys can monitor it from there. Yeah?
If it goes into alarm, will that send a signal to our Tritium screen that it is in alarm?
It will have the alarm into the Jace that we're providing, and it gets from there to YAMAS. From there, I don't know what they do with it. I'm assuming it gets there.
Okay.
But I can tell you how far our stuff goes, and
Yeah.
I'm assuming they have those displayed though. So that typically what they'll have is a flow alarm and a jam alarm are the two types of alarms. A flow alarm indicates that the pressure drop across the valve is not being met. A jam alarm means that it's trying to drive the valve, but the valve does not appear to be moving. Every one of these has a potentiometer in this little piece right here that feeds back a resistance value into this circuit board. That way it knows as it rotates that arm, it knows exactly what position the arm is in. It uses that feedback of the resistance that actually sends a voltage through it, so it gets a voltage signal back indicating it's open to a certain level, and there's a flow curve programmed into each of these. That's a custom flow curve calibrated at the factory to indicate exactly what flow it will have at that position if the pressure requirements are met. So does that make sense as far as those three things have to be the case. It has to be in the right position, pressure has to be across it, and it has to be able to move it to get there. That's the basics of what a Phoenix valve is and how it works. This specific model has a ridge inside of it and a gasket on here. This is a shutoff valve. I don't know for sure if you guys have any on here. I don't think so. I didn't see any on the sheets. Most of yours will be smoother here, and there will be no gasket on this. And basically that means there's a minimum flow that when the valve is completely closed, you're still getting some flow through the valve. Typically you have your minimum flows anyway, so you don't need zero flow through a valve unless you have a vivarium area that needs shut off for cleaning or stuff like that. In this case, you have just standard lab flows. One of the other things to be aware of is the type of valve. I only brought in an aluminum one because I don't have a demo one that's a coated valve. But on all of your fume hoods, the valves are actually going to be a brown color. So if you see a brown colored valve, it looks like it's powder coated in brown coating. That's actually a chemically treated valve to resist any corrosion and those kind of things from chemicals that are used in the fume hoods. All of your other valves are going to be aluminum. Typically your supply valves are going to have a thin layer of insulation around them. And that's just to try and maintain the temperature of the air as it goes through into the airstream and then into the room. The exhaust valves typically don't have insulation. On occasion, the functionality of a supply valve is needed in an exhaust valve scenario, so you may see insulation on an exhaust valve. It's not a problem, it's just insulating that on the way out. It doesn't cause any efficiency or any benefit at all. It's just because of the functionality of the way it needed to interact with the other valves in the room that changes that. But typically, if you see a bare one, it is going to be on the exhaust side and insulated or on supply. And then brown ones are the hoods. So we have a lot of these through the building. I don't have the exact numbers with me. And the only other equipment that we provided is actually fume hood monitors and ZPSs on the fume hoods. So when we do a walkthrough, I want to show you guys one of those with those set up on it, rather than just holding one off to the side, because I want to have power on it so you can see what the buttons do. From the factory, these have a maximum and minimum level that they are set up to based off the design flow numbers. Those can be pushed a little bit. Typically those are set up in balancing. The way these control a room overall is through offset control. An offset is where you keep track of how much air you're pushing in the room and how much air you're pulling out. That number is the equivalent to the air that's being pulled or pushed out of the room through other areas. So typically that's under doors, around edges of doors, basically any leaks in the walls, those kind of things. So the airflow offsets are designed with specific numbers in mind, intending to reach some kind of pressure range or whatever. But if the construction of the room is slightly off, it may or may not reach that pressure range. I don't know what the requirements are on this project. They may be doing some adjustment on that so that the offset numbers may or may not match the design on the drawings. Usually they do for lab spaces. Usually they're not critical pressure control. If they want to do pressure control, then they'll need to adjust those numbers, those offsets, so that they're more positive or more negative to meet the needs of the way the room was built. Does that make sense to you guys? So the offset is, you're pushing in 300 CFM more than you're taking out. So that means that 300 CFM is actually bleeding out under the doors or through the walls or anything like that. The other option is if you want a negative space, you're sucking out 300 CFM more than you're pushing in. So you know that amount of air is sucking underneath the doors or through the walls or whatever. Basically, that's your offset control. It's fairly simple. As long as you have maintained your pressures across the valve, like we said, and the valve is in the correct position, it's not in flow alarm or jam alarm, then you can be fairly certain that room is getting that offset for the air. So if you have that offset, you know it's getting the air into the room or out of the room somewhere. Sometimes if
How do we know if it's supposed to be in a positive or negative effect?
That would be based off the design and the drawings.
If I may, most rooms that you have here, I don't know of any positive pressure rooms offhand. They're all negative. And the offset is averaging about 200 CFM exhaust oversupply.
Is that something you routinely monitor every year, or?
If it is set up correctly, then you will not need to worry about it unless you get an alarm here. The Phoenix system will adjust.
It'll read the pressure in the room, tell you.
It's actually
we don't have a quantified pressure in any of these rooms.
Okay.
There is not a number or a value that they're searching for. They just want it basically negative.
And if you're controlling the offset, you know overall it's going to be negative. Because if you know you're taking out more than you're putting in, it's going to be negative. Unless you have some fan somewhere pushing air in that you don't know about. But that's how it's going to work typically. You don't need to worry about it in the future unless it's a problem somewhere that you see, okay, this lab is always blowing air out into the hallways. Then you can see sometimes there's a dynamics issue where there's more negativity in the hallway because of some other thing down the hall. But typical lab spaces are not critical pressure control. They get a general offset and it works. When you run into critical pressure control, you have to have sealed doors, sealed rooms, everything has to be sealed up. Once you have T-bar ceiling and open plenum above there, you're not really going to be able to control pressure. That's just the way they work. So these aren't designed as pressure control spaces. But overall, it will still follow that path just because of the offset. Does that make sense? So, let's see if I can remember where I was. Okay, so the cone can drive in and out, and like I said, this pressure, as long as it's right, will press down the spring just enough, because the spring is designed with a specific resistance in mind, so that no matter what the pressure is, as long as it's within the range on the upstream side of the cone, it'll hold just the perfect position. The airflow on these is critical. The direction is critical to be able to maintain that. Obviously, this cone has a more rounded side and then this more flat side that kind of comes back. So the airflow is coming this way on this valve. It has to hit the rounded top of the cone first. Typically they throw an arrow on the outside of the valve so you can see which way that's going. So if you're in an exhaust scenario, the room side is over here and airflow is coming across there. If you're in a supply scenario, this side of the valve should be pointed up at the air handler, and your room side is over here. So as airflow comes across here, it hits the cone, and the spring holds it in the right spot, and just enough air comes around the sides to get through. And these that's your typical stroke on these. So you've got a couple inches on the end where the end of the cone is, but you will need, obviously, a good 6 inches on that side of ductwork that's not in the way of hitting something. One good thing about the Phoenix valves and any Venturi valve design is that if you have airflow that's going around the bend real quick and coming in here, it does not have any problem maintaining the correct values coming through here. You can have a 90 right on the end of this as long as this bar isn't hitting it, and it'll maintain the flow correctly. But that 90 is adding restriction to your system, so you need to be aware of that to make sure that you still have your pressure drop. Putting in as many 90s as you want is not a problem for this, it's a problem for your fans. So these don't care how you turn the air coming into them, how long it is before or after, whatever. But if you have more straight runs, then that means that you have less fan effort to get the same pressure drop across the valve because it's not fighting to get around the 90 first. Does that make sense? That's really the basics on these. There's another type of motor that is a black kind of pistol shape. I don't have one of those with me today. If we have any ceiling tiles out that I can point at one, I can show you. This is a low-speed actuator. It's just a standard damper motor style. The black pistol ones are used on all of the fume hoods because they are a high-speed actuator. They have large capacitors on them in order to get the speed they need to respond to somebody sliding the hood up and down. Because anybody can come in and slide a hood up, and you can slide it up pretty quick, a lot faster than most, or any little damper actuator is gonna move. So you need to be able to respond to that and have the correct flow extremely quickly to maintain the safety of the rooms. That's why they'll have these big black actuators on there that are a linear stroke actuator. They get to, I think it's 90% of the flow within 1 second. And then it's maintained in the room and your offset's maintained. Everything responds very quickly on those. If you see a style with this, it means that there's probably no hoods in the room and they're just maintaining offset control based off temperature. So it doesn't need to respond quickly because nobody's going to come in and slide a sash up and down. So that's the basic description of this. The next thing I'd like to do, if we have some time, is to go and look at a hood and kind of show you what those controls look like. Is that good with you guys? Any questions before we go? Yeah.
So in every room, there's one on the supply and one on the exhaust?
I'd have to look at the drawings before I say yes, because they can do whatever they want. You typically have an exhaust and a supply, and then you will have maybe a hood. If you have enough hoods, sometimes you need additional exhausts or supplies. Typical scenario is a hood with an exhaust and supply, but I don't know how many typical scenarios you have here. I'd have to go through the drawings to be sure. Any mechanical drawing can show you where the Phoenix valves are, and you can just look up, okay, those are all the supply duct and exhaust duct. You can get some really complicated scenarios.
Some rooms could have two of them.
There's a lot of rooms that have
Two supplies.
two supplies, two JXs or general exhausts, and multiple hoods.
And a general exhaust is an exhaust that takes effect if all the hoods are closed down. Because if all the hoods are closed down and you need to add more supply, you've got to get some of that air out that you're adding.
Yeah.
So if you have a cooling demand in the room and all the hoods are closed, then supply has to come up, so you got to have a general exhaust to be able to make room for that. That's what a general exhaust is used for, really. It's for when hoods are closed down. If hoods are open, typically the general exhaust is down low, and the supply valves are already up high because it's trying to keep the offset, and it's just modulating the heating valve to maintain temperature.
If I may, there's
Yes.
several variables then that we're looking at in controlling the room. The supplier is controlling not only ventilation, but also temperature control. So whatever air is necessary to control the temperature of the room. The general exhaust and fume hoods work together to make it negative into the total room. The fume hood will change values if the sash is open or closed, and if rapidly closed and open, then everything that will have to respond accordingly.
Yeah.
The Phoenix system is smart enough to add up all the numbers and command the valves to maintain your offset totally to the room. Is that
Yep. Yeah, that's correct. And there may be some scenarios where you have, I don't know for sure in this building, but if you have enough hoods in a room, sometimes you don't have a general exhaust because your minimum flow that you need when all the hoods are closed is your cooling load as it is, so you don't need to add more supply. So I have seen scenarios where you have just supply and hoods with no exhaust. I don't know if you have any here, but typical is supply and
I don't
exhaust.
think we have any of
Okay.
those.
So typical is supply, exhaust, and hoods. Make sense? Yeah.
What type of service or maintenance do you generally see on these type of-
Scheduled and failure rates, different type of things, so what's gonna fail on these?
As far as failure rates, I'd have to look up information on that. I honestly don't have any of that with me. I have seen some of the motors fail on occasion. I believe the warranty on all of these parts
Okay,
is, it's either 2 or 3 years. I believe it's 3, but I'd have to look it up to be sure. And typically, we swap them out pretty quickly. They did come with, originally, it was before your job was ordered, but the high-speed actuators had a plastic backing, which probably 10% of the valves snapped off. They have made a replacement that's a metal one. All the new ones come with metal ones on them, so all of yours have metal ones on the back. But if for some reason any of them do break in any way, we just get those in and swap them out. Maintenance in general, there's no scheduled maintenance on these because the plastic bearings on here, like a Teflon coated thing that's just there's no Zerks or anything to fill with lubricant. And typically, they just run unless you see them fail in jam alarm or flow alarm. Well, flow alarm is typically an outside issue. Jam alarm is internal issue.
Is there any calibration on it that you need to do after?
After it's done, though,
Okay.
they're set up and they run. If you start noticing a room having issues with flow control, typically what you'll need to do is obviously first check for alarms. And then if everything looks good and is communicating, then you need to just look at the overall room and see, is there some other dynamic that has changed? Is there somebody that threw in an exhaust fan somewhere that isn't taken into account? A lot of times lab facilities, that people like to throw in a piece of equipment that hasn't been accounted for, and they'll hook it up to wherever. Yeah. You've seen that clip. So if the offsets seem wrong, sometimes that's what's happened. But typically calibration and verification on flows, these things go for a very long time.
What about the boards, if they fail?
The circuit boards, if they fail, those are covered for the same warranty period as all the other parts. And typically we can just get another one of those and swap them out. The board stores the flow curve for each of these valves.
So they
Based
have
off the serial
individually set up with a flow curve.
Yes,
Okay.
and the flow curve we can reload to any board and throw it on there. And the flow curve is stored based off the serial number of the valve. So we can look at the sticker that's on the side of the valve, find the serial number. The factory stores those. I don't know if they ever purged the records. They haven't for the last 10 years or so that I know of. I believe they just store those forever because it's just a simple file for each one, and they like to have that. So they store those forever, and if for some reason the board is toast, you reload the flow curve in a new board on there and dump the parameters in it, link it up, and it's good to go.
How about your cost difference if you do have a board go bad? Is it just versus just the whole valve?
Typically, it's definitely worth replacing a board versus the whole valve.
Is it?
Besides the fact of the parts, the labor for ripping this out of the ductwork and putting it back in and all that fun stuff is quite a bit.
Okay.
I don't know the numbers on it. I can look it up and get that info to you guys. But the boards, I believe, are about a third of the cost of the valve overall. I think it divides up about that. The valve body and the cone assembly and everything in here has quite a bit of cost to it because of all the patents and the design and the machine processes they use and that kind of stuff. Another thing that I forgot to mention earlier, they are designed either to be vertical or horizontal only, one or the other. You can't take a horizontal valve and turn it vertical or anything like that, because this spring has to be a little bit different in those. Because in this path, the spring has no weight sitting on it. If you have it going with a vertical downflow, all of a sudden you have the spring weighted down by the cone. So it has to adapt for that, so they make the spring a little bit stiffer, so that the air pressure across here makes the same distance change as it would if it was horizontal.
Is there a difference on the indexing? You know, which direction is?
Yes, because if you flip it up the other way, obviously the spring goes,
I mean, flat if it's turned.
oh, no, rotated like this,
Right, rotate it.
no. That, it doesn't matter, because the cone is equally weighted around
Like
this
this.
round.
Yeah.
So, they're either horizontal, vertical upflow, or vertical downflow. So, they make sure that those are all right and working in here, but if for some reason in the future you guys find one that you need to swap out or whatever, or there's problems with it, then, or if you need to get higher flow, you need to make sure to use the right type. Because you can't just grab one from some other place and shove it in there if it's not the right orientation, all of that kind of stuff.
How can you tell?
They actually have a sticker on the cone, but if you look at the label on it, it says vertical upflow, vertical downflow, or horizontal only. It actually says it on a big label with the arrow and everything on production valves. This one's obviously a test demo one, which you can swap out the cone at any time and change which one it is. And they have a big hole. Yours don't have holes in them like this. I know. It'd be really nice to have a nice big window on every one of them so you can look in there and say, oh, look inside. But
What about you said the pistol thing, the pistol?
yes,
So there's capacitors on that. What's the life expectancy on? Is it on the board itself?
they're
Like
on the
small
circuit boards.
capacitors?
They're
Okay.
actually very large capacitors.
Okay.
So those capacitors are on there. There's two different versions. Typically there's a fail in place model and a fail in any position, like you determine the position where you would want it to fail. The fail in place ones have fewer capacitors because they just have enough capacitors to make the damper move back and forth as it needs to. If it's a fail in a specific position one, it'll have additional capacitors because it needs to store enough energy so that if power goes out, it can go to fully closed or fully open or wherever you wanted it to fail to. Typically with a hood, in a failure mode, a fume hood, they want it to fail fully open so that it gets as much air out of there as they can. And you know your laminar flow is not correct on the hood, and then you get an alarm on the hood, so you know it's not the safest thing, but it's more exhaust than not.
So, will there be points available that will be able to use to force the cone over the place?
I know that they're exposing the set points for the room. Typically, in order to force things, we don't want to override a specific one because then that's messing with offsets, so we don't expose that to people. What we expose is the set point for the room. So if you make the room set point high enough, then it'll go down to its full heating or whatever. You can make it go to full cooling if you put it, make the set point low enough, and that's how you'll drive the room as a whole. As far as forcing it, we don't typically expose that because it is a safety issue.
Are these all 24 volt supply then?
Yes. So 24 volt AC supplies power to these and the fume hood monitors. Some of the older Phoenix stuff was before they went to the lawn-based circuit board and everything, when they had the analog age, they had a plus and minus 15 volt DC supply. So I don't know if you have any old Phoenix stuff around on your campus, but this building is all 24 volt AC. If you have the high-speed motors, they actually require a 100 VA transformer for each high-speed valve because of the inrush current when you power up those capacitors.
And that's all the damn codes.
Yes, all of your fume hoods, and any room that controls a fume hood, its supply and exhaust is also going to be on a high speed because it needs to be able to respond to what the fume hood changes are. Because fume hood responds to the sash position. Then all of a sudden, okay, you've got more exhaust in the room, you need your supply to go down or your general exhaust to go down or up or whatever, whichever way you need to go. You need all of those to respond quickly. So in a lab with fume hoods, you're going to have high-speed control on every one of the valves. The only one that I've seen in a fume hood lab that is not typically high-speed is a snorkel. A lot of times those are constant volume. So they don't need to be high speed in any way. They'll put a low speed one on there and say, okay, just be in this position. The other stuff responds quickly to take care of the flows. Yeah?
Do they operate on a 0 to 10 volt? The actuators operate on 0 to 10 or 4
The actuator does not. The actuator is a modulating or a 3-point floating, but it gets feedback from the potentiometer to know right where it is. So that's how it knows where it is and gets to the right position, is it sees the voltage of this potentiometer change. So it knows, okay, I've got this in this position, and it drives it until it gets there. And then it stops. The signal from the fume hood monitor up to the Phoenix valve actually is a 0 to 10 volt signal. So it sends a 0 to 10 volt signal into the card on the circuit board. And the card then says, I know where I need to send this motor. So it drives it until it gets there. And then it stops. Does that make sense?
Yeah. Does that circuit board have a reset button on it, or?
There's no resets on these. Typically, to reset the card, you actually unplug power from it, turn the power off, wait till all the lights turn off, turn it back on. On your high-speed cards with all the capacitors, turning it off and waiting for it to it can take quite a while for those capacitors to discharge. So usually I'll turn them off and go away for an hour or two and let them discharge and then come back up. But you don't have to reset these unless they have some weird issue that you can't figure out if you can't communicate with them or whatever. Typically they just sit there and run and everything's happy. And a reset typically won't take care of either of the alarms, because typically the alarm for a flow alarm is externally, don't have pressure across the valve. The reset is going to do you no good.
But you'd see that on more than just one. If you have
Correct.
an exterior valve.
It depends on how short you are. Sometimes, if it's just the one at the end of the line,
That's true.
you can have it on just one. It is possible. typically you'll see your whole system be low, and you'll have an alarm from your pressure in your ductwork before you would see a flow alarm. But it can be just one if for some reason it was designed with a certain scenario and all of a sudden they're taking more exhaust out in the middle somewhere, and that last one at the end of the line just doesn't quite get what it needed anymore. But that is correct. Any other questions?
Is the board fuse protected?
They actually have circuit breakers on all of the transformers feeding these. So they're 100 VA circuits coming off of the transformers. There's little 100 VA circuit breakers on each transformer. I would have to look at the drawings to be sure which models they used. Typically, for a lab, I'll use the larger transformers that have individual circuit breakers next to it. They may have used the individual transformer and circuit breaker combo, so they have individual transformers per valve or whatever. But they are circuit breaker protected.
And you mentioned something earlier about the power loss failing to open. Do you know if that's set up here at this building? And then my other question on that would be fire code, because doesn't it get outside? Would there be a fire damper anywhere?
It goes to the position that it fails the safest in. Typically, every job I've done that has fume hoods, the fume hoods are not supposed to have fire dampers between them and the exhaust. But if they shut the fans down, it does no good anyway. So it depends on what they're doing with the fans. These go to the position they need to be in, whatever it is for safety. Any of your low speed stuff is going to be fail in place, period. Because it knows this was the temperature demand in the room, there's no reason to go wide open, we already know we have our offset, everything's good. Fume hoods are the things that kind of change the dynamics of what you're doing. When you have fume hoods in there, typically you want your fume hoods to fail open. That way, if somebody messes with the sash, it still has as much flow as it can get, so everything's happy. And then that would mean that your other flows need to fail in the correct positions as well. So your jets typically will also fail open to get exhaust out of the room in case somebody closes down the fume hoods and your supply fails open. But that depends on the drawings, what the engineer asked for. There's a lot of variables, so it's not a hard, fast rule. But that's how those work. And so fire code is taken care of by the fans. We just put them in the safest position we can for making assumptions of not knowing what's going on in the building. Anything else?
Is there a service, 24-hour service rep or anything if a guy's working on it at 3 in the morning?
Yeah, we do have our office number you can call and get directly through to a pager that we have somebody on call 24/7. And we get the page, they call in and get the message from you. There's actually 2 or 3 people that make sure that that happens. And then a technician can come out and take a look at it and help you guys, or answer whatever we can. Try and get you guys taken care of. Anything else? Okay. Well, do we want to go take a look at a fume hood so you guys can see what they look like, make sure we're on the same page? Okay, this is obviously a lab. This is a great one to show you some stuff because we're missing the ceiling, which means I can show you where the valves are. So this lab only has the one fume hood in it. The fume hood monitors are recessed into the side of the fume hood right here. It's got a display showing you the calculated flow across the face of the fume hood. That is attempting to maintain 100 feet per minute unless there's nobody around for a little while. I'll explain that in just a minute. Right now you can see it's getting about 93. That actually is within tolerances for these, and that's safe. You would see an alarm if there was a problem. You can see right here it says standard operation. That light is lit up. That means that this motion sensor has seen somebody in the last little while. If we keep people far enough away from it for long enough, it can go to setback. As long as they have that set up, which with these, that's typically how they get set up. And then it would attempt to maintain 60 feet per minute across there, minimum. The only difference with that is if you have it closed, it's already down at its minimum. So typically it's just going to maintain that 100 feet per minute even if it goes to setback when it's closed. The setback is really when somebody leaves it in a different position. So you can see that went back up to the 96 feet per minute across there. Obviously you're pulling a lot more air through there now. There's only 2 buttons on this thing. One is for emergency exhaust. That shoves the Phoenix valve to its full flow position. So you push that button and all of a sudden you get 200 feet per minute here, which is not necessarily a good thing. The reason they have that 100 feet per minute design is so that the flow is slow enough that it doesn't create turbulence, but fast enough that it still pulls everything that way. So 100 feet per minute has been found to be the best number for having somebody here working and having all this fumes and everything go through the hood. If you get up too high, you can create little turbulent eddies and some can creep back out. So emergency exhaust is just when, okay, I've got to get as much stuff out of there as I can from inside there, and you just push emergency exhaust. You don't really need that normally. I've never seen anyone actually need it or use it, but it is there just to be there. If it's in alarm, there's a mute button so you can make it stop beeping at you. That's really all there is to the buttons as far as function. Obviously you can see that standard operation light went away. So it's no longer in standard operation. Somebody's got it in emergency mode. Go back out, goes back into standard mode. If the pressure is not across the valve correctly, then it would actually be in flow alarm. The bottom light would be on. And you'd hear it beeping and people would be getting annoyed or they'd be pushing mute buttons. One thing lab people are very well aware of is that there's always a mute button, you push it and then everything's fine, right? Stuff's functioning just perfectly once the mute button's pushed. Okay, so this is a ZPS, or Zone Presence Sensor. This actually has a camera that's watching this floor space. It's a camera instead of just a motion sensor, so that it can actually calculate a specific area. It can be adjusted through a USB port, and if somebody places an object here, if that object stays there and doesn't move, then it recalculates the area to make sure that it's not monitoring that. But all this is doing is trying to save you energy when people leave their hoods up. That's a common problem in most lab scenarios. They leave the hoods open all the time. You're wasting exhaust because your fans are running up higher. If you can get your users to keep these closed, then you can keep your flows as low as you can, and your ZPS doesn't need to do anything. It'll still tell it to go to standby, but it'll already be at its minimum, so you won't get down to that 60 because it can't go below its minimum. But that's your best energy savings, is close the sashes. Now the ductwork comes out of here in stainless steel and goes up and around, and there's a hood valve for this hood right here above the light. So if you look up here, you can see this brown coated valve.
You guys see it right here, this coming very well.
And you can see the black actuator on that. That's your high-speed actuator. So watch that actuator as I drive this sash up and down. Should be able to see it drive. Or maybe so short of a stroke because it's a very small hood. So that's a typical hood valve. Right here, we have a double exhaust. So some of these, because you need more airflow through some specific grills, will have 2 valve bodies instead of 1. The motor is obviously still strong enough to drive the 2 valve bodies simultaneously with that linkage, but that can get more airflow through. Typically when you need more airflow than that, and you're going to a triple, it's actually a separate double valve and a single valve that are linked together that tell each other what to do. See if we can find the supply in this room. Where's the supply register? Over here? Okay. Here's a double supply valve, and you can see that this one has your insulation on it, like I was saying. So this is bringing your air in, and you've got a heating coil that's driven by that supply valve as well. That's actually from an analog output from the valve, so it is a 0 to 10 signal to that heating actuator to be able to maintain your space temperature in the room. It's driven off the thermostat over here. basically, this is just reading the temperature in, and you get it set to whatever. You guys can override stuff so it can't be driven from the slider. The slider can give you warmer or colder, but only if you guys have enabled it. I'm not sure what the policy is here, what you guys do. Typically we have that enabled to like a plus or minus 2 degrees or plus or minus 3 degrees. But you guys can also override it from the front end and say, this is your set point, deal with it.
So what are the increments on the slider then, as far as?
It's actually set up to go full swing.
You
So-
can feel it click, 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 click.
Yes.
Can't you?
But that's not a specific increment because you could change this range to be plus or minus 2 or plus or minus 3 or plus or minus 5 or whatever.
Okay.
So it depends on the resolution, on what you put in there. And that's really the basics of how this room functions and the equipment in here. Is there questions on the equipment that you guys have seen? You can actually see the exhaust port is exposed right there and see the lights flashing on it normally at the moment.
So the lights, explain to us again what the lights are.
Okay, one is power, another one is communication. The blinking is just saying that it's got a heartbeat, it's functioning. If you see the lights where they're all solid, then that's typically a bad thing. But the blinking lights means they're actually communicating and they have a heartbeat, the logic is being processed.
So the red light is the heartbeat,
Yes, I believe so.
and then the amber light down on the bottom of the card.
I always look at them on the labels. I can show you on the one. They actually are labeled on the circuit board,
Okay.
so I never remember personally unless I look at them. But when there's a problem with the card, you can go up and look at them and you see blinking, then typically that's a good thing.
So everything prevented from the hood and that other return over there, that is all on outside?
Yes.
Because it doesn't go to a heat recovery or anything?
It all goes to heat recovery.
I was gonna say that's a question for Ken. Yeah.
Even the vent hoods go to heat recovery?
It goes through ladder exhaust fan 1, 2, and 3. The only one that doesn't go through is ladder exhaust fan 4, and that's because it's got some ugly nasty in it. I know, that's radioisotopes. So
Yeah.
So in this room here, the return here is not controlled on the valve, it's this return here.
This is actually a supply
That is a
register,
supply.
and that's a supply, and then that's an exhaust over there. Typically in a lab, you don't do return, you do actual full exhaust. So all of your stuff going out, that would be an equivalent of an exhaust
Okay,
register.
so where's the supply valve for these?
That's actually right there. So it's coming through, you got your coil, and then you got your duct coming across and hitting all those registers. So that supply valve is right here above this light. And those should be on the drawings, showing you basically where they are, what size they are, all that kind of stuff. And if you notice on this one, like I said, it's insulated, so you know it's designed as a supply one. The exhaust over here, you can see no insulation on it, just straight aluminum body. That means it's general exhaust, typically, or a snorkel. And then the other one over here, that little one, was brown coated. That meant it was a hood, because it's coated for chemical resistance. Does that make sense?
Yep.
Okay? Any other questions on the Phoenix stuff?
Have you ever run into distortions or noise when you get it unbalanced or a erratic static pressure from your handler?
Noise as far as just audio noise in the room, or what?
Well, usually it's typically in the valves you'll get either a whistle or a hum.
Yeah.
Where they are spring loaded, I don't.
It's
know
not
if
an
that's
issue with the
dramatic.
functionality of the valve. What they actually have for that is if you have a scenario where they are too noisy, they have a, what they call a neutralizer, a sound neutralizer that gets put in the ductwork beforehand. And so before it gets into the valve, you have this neutralizer right on the end that isolates the sound waves and makes it quieter. So if there are issues for that, we have a product that we can sell that you guys can put in the ductwork and everything's happy.
I would imagine that there would be a pressure drop involved in that, so you have to make sure your system can handle that sound attenuation.
Yes, that's the case with anything.
Typically, you're saying you're putting that sound boot basically ahead of the airstream or behind the airstream for the space or for the duct. For the high pressure
Typically it's in the space. Towards the space is where it goes. Because you want to isolate it from transmitting into the space. So, exhaust side is actually, you know, ahead of it. And that's the one I think of most because usually that's the one that they forget to insulate ductwork or whatever because they're not worried about controlling the temperature on the way out, or it's really close to the registers or whatever. So typically it's more noticeable on exhaust when I've seen it. I've had buildings where you have, 300 valves and don't see a thing.
Right,
And
yeah,
buildings where you have 4 and you hear it. And it's like, well, so it has to do with the exhaust ductwork design in general. So if it is an issue, there are product solutions. And then you'd have to make sure that you balance out your ductwork pressure ratings and all of that stuff, make sure you can handle it. Make sense? Okay? Any other questions? Okay. Well, thank you guys. I will let you get turned over to Lee or whoever else.